This is analysis sequences. Now, a sequence of real numbers is a succession of real numbers in a definite, predictable order. Like example here. Well, let a of n equals 1 over n, where n is given in our positive integers. Then a of n from n equals 1 to infinity is the sequence here. 1, 1/2, 1/3, 1/4, and so on. Another example here. Minus 1 to the n of 1 over n, where n equals 1 to infinity. We'll get this alternating series here. Minus 1, 1/2, minus third, 5 fourths, minus 1/5 and 1/6, and so on. Sorry, I meant 1. I put 5. And an example here does not necessarily have to be numbers. They could be trigonometric functions, like x of n equals cosine n of pi, where n is again in our positive integers. Then we let x of n from n equals 1 to infinity, and this is the sequence here, minus 1 plus 1 minus 1, and so on and so on. Now the sequence of 1 over n squared as n equals 1 to infinity is 1, 1/4, 1/9, or just 1 over square number. Now is a same example. If we skip the first 4 terms, then our sequence would be n equals 5 to infinity of 1 over n squared. So it would be starting from 1 over 25, 36, and so on. Now another example. A of r equals n plus minus 1 to the n over 1 over n, where n is contained in the positive integers. So this time we'll get 0, 2/2, 2 2/3, 4 1/2, 4 4/5, and so on and so on. Now, as a of n goes to infinity, as n goes to infinity. Now, where a of n equals 1 minus 1 over n, where n is again our positive integers. This will give rise to our sequence given here, as a of 1 tends to 1 as n goes to infinity. Which makes sense, because if n gets larger and larger and larger, this number gets smaller, and as it approaches infinity, we can pretty much say that this is 0. So it equals 1. Now here's an example. We'll let an equals n over 2 plus minus 1 to the n of 1/2, where n is our positive integers, where x is an integer part of x, i.e. it is the greatest integer, such that p is less than or equal to x. The sequence now starts at minus 1 and 3/2, 1/2, 5/2, 3/2, 7/2, 5/2, 9/2, and so on. Now the 2000th term, a 2000, is 1000 divided by 1/2, and 200,000th term is 100,000 plus 1/2. I meant plus 1/2, not divide. Now, despite the fact that the size fluctuates, it still seems reasonable to say that a of n goes to infinity as n goes to infinity. Now, if we plot against n, a of n, our values for a of n, as it increases with our n, we get a graph as such for our points and going in this kind of direction. Now, what properties are necessary if a sequence tends to infinity? Well, if we draw a horizontal line above the n-axis and all but the first few terms are above this line, if we draw a line at a height 100, say, above the n-axis, then all but the first 201 terms are above. In general, if we take any positive real number a, however large, and draw the line at a height a, then all but a finite number of terms of the beginning of the sequence are above the line, i.e. we can find that n such terms, a of n, n plus 2 are above the line. Therefore, sum n such that a of n equals is greater than a for all n contained in this n. The value taken for n will depend on the size of a. For example, if we choose a equals 10 in the above example, then we notice that a of n greater than 10 equals a for all n greater than 21, i.e. we can use n equals 21 in this case. For if n is greater than 21, then n is greater or equals to 22, and so on. So our sequence here will get an is n over 2 plus a minus 1 to the n of 1/2, which is greater or equal to 22 halves plus minus 1 to the n 1/2, which equals 1 plus minus 1 to the n over 1/2 is greater than 10. If we take a equals 100 and an is greater than 100 equals a for all n greater than 200, shown here. Now, which would effectively, no, sorry, that should not have been an equal. That's a minus there. I thought that didn't make sense. Yeah, I kind of screwed that up a bit because it's obviously not greater than 10. But hopefully you should get the gist of this. Now, if we show this, what we were saying with A1, A, N1, N, and so on, of our axis A of n as n increases, we show, as before, our graph here for the sequence. Now, in general, given that a is greater than 0, we can always find a corresponding n. If we choose n to be the smallest integer such that n is greater than 2a plus 3, then our sequence is given as such. N over 2 plus minus 1 to the n 1/2 is greater or equals to a plus 2 plus minus 1 to the n of 1/2 is greater than a. So for all n contained within this n. Now, since n for all n greater than this n, since n is greater than this n, implies that n is greater to equal or equal to 1 plus n, greater or equal to 2a plus 4. Now, clearly arguments of the same type could be used for all sequences in the example below. Now, in this case, given any a is greater than 0, all we need to do is choose n to be the smallest integer greater than a. Then a, for all n greater than n, and n greater or equal to n plus 1, we'll get this sequence here, where we show that n is greater than a. Now, a sequence for a of n of real numbers tends to infinity if and only if given a greater than 0, however large, there exists a corresponding positive integer, n equals n of a, such that a of n is greater than a for all n containing n. We write a of n goes to infinity as n goes to infinity. Here we have written n as a function of a. Now, to emphasize the fact that that the value chosen for n depends on value given for a initially, in general, larger values of a give rise to larger values of n. Let a of n be a sequence of real numbers, then we say that a of n tends to sum L as n goes to infinity if given my epsilon greater than 0, there is a corresponding n as a function of epsilon, such that the absolute value, magnitude of an minus L, is less than our epsilon for all n contained within our n, i.e. L minus epsilon is less than a of n, which is less than 1 plus our epsilon for all n contained within our n. So we write as a of n goes to L as n goes to infinity, and we can write this in the limit notation here, limit as n goes to infinity of a of n equals L. Now, here's a quick example here. Now an a of n equals 1 minus 1 over n, where all the n is contained within the positive integers. We'll get 0, 1/2, 2/3, 3/4, 4/5, and so on. So we see that an is within a given arbitrary small distance of 1 for all sufficiently large n. For example, 1 minus 1/2 is less than a of n, which is less than 1 plus 1/2 for all n greater than 2. And 1 minus 1 over 100 is less than a of n, which is in turn is less than 1 plus 1 over 100. Now for all n greater than 100, if we take a pair of lines across the graph, one at an arbitrary small distance, epsilon, below L, and the other one, epsilon, above 1, then the points representing a of n are between the lines for all sufficiently large n, i.e. 1 minus epsilon is less than a of n, which is less than 1 plus epsilon for all sufficiently large n, as shown here. Now for given my epsilon greater than 0, however small, we notice that 1 minus epsilon is less than a of n, which is less than 1 plus epsilon for all n greater than 1 over epsilon. If we choose n to be the smallest integer such that n is greater or equal to 1 over epsilon, then 1 minus epsilon less than a of n, in turn less than 1 plus epsilon for all n greater than n, i.e. our magnitude is less than epsilon for all n greater than n. Now we let, as an example, we'll let a of n equals n squared plus n plus 1 over 2n squared plus 1 for n contained within our positive integers. Now it seems reasonable to assume that a of n goes to 1/2 of as n goes to infinity. To justify this, we'll notice that a of n minus 1/2 equals this minus 1/2, because this is our a of n here, a of n minus 1/2 equals this term here. So our absolute value is less than 2n plus 1, 2n squared is less than 2n plus n, 2.2n squared, which equals 3 over 4n for n greater than 1. Now and therefore epsilon is greater than 0. So here it is giving our bounds. Now a is the maximum 3 over 4 epsilon. Thus, if n is chosen to be smallest integer such that n is greater or equal to max 1 over 3 over 4 epsilon, then a of n minus 1/2 is less than our epsilon for all n contained within n. Now our standard limits are n to the alpha. As n goes to infinity, n to the alpha goes to infinity if alpha is greater than 0, 1 if alpha equals 0, and 0 if 0 is greater than alpha. For if alpha is greater than 0, n to the alpha is greater than our uppercase n to the alpha, which is greater or equals to a for all n greater than n, where n is the smallest integer such that alpha logarithm of n is greater or equal to the logarithm of a, i.e. n is greater or equal to e to the ln of a over alpha. Now hence if n to the alpha goes to infinity, as n goes to infinity for alpha greater than 0, when alpha equals 0, n to the alpha equals 1. Hence n to the alpha goes to 1 as n goes to infinity. When 0 is greater than alpha, we'll write beta equals minus alpha, so that beta is greater than 0. Then we can write this as such. As n goes to infinity, since n to the beta goes to infinity as n goes to infinity. Now with a to the n, as n goes to infinity, a to the n is infinity if the a is greater than 1, 1 if it's equal to 1, and 0 if the magnitude of a is less than 1. Now, and a of n does not tend to any limit if minus 1 is greater or equal to a. If a is greater than 1, we can write alpha equals 1 plus h, where h is greater than 0. Hence, we'll get this series here, sequence here. Since h is greater than 0, 1 plus n to the h is greater, tends to infinity as n tends to infinity. If our alpha is bound between 1 and 0, then our a is 1 over b, where b is greater than 1. Thus, a to the n is equal to 1 over b to the n goes to 0 as n goes to infinity. Now, since b to the n goes to infinity as n goes to infinity, if a equals 0, a to the n equals 0 for all n, and a to the n goes to 0 as n goes to infinity if minus 1 is less than a and a is less than 0, then minus our absolute magnitude of n is less than or equal to a to the n, which in turn is less than or equal to our absolute value a to the n. And a to the n goes to 0 as n goes to infinity, because our absolute magnitude of a is between 1 and 0 by the sandwich rule. A to the n goes to 0 as n goes to infinity, and if a is less than or equal to minus 1, then a to the n equals minus 1 to the n multiplied by absolute magnitude of a to the n. Since a to the n, magnitude a to the n is greater or equal to 1 for all n and a to the n, and it cannot tend to any limit as n goes to infinity. Now, a to the n over n to the alpha, for a greater than 1, alpha is greater than 0. It has already been shown that a to the n goes to infinity as n goes to infinity, as n to the alpha goes to infinity as n goes to infinity. But what happens to the quotient? Well, a to the n over n to the alpha goes to infinity as n goes to infinity for a greater than 1 and alpha greater than 0. Here's an example to demonstrate this. If we take a close to 1, if we take a close to 1 and alpha very large, then this seems somewhat unexpected. For example, we claim that this number here, 1.00001 to the n over n to the 1 0001 goes to infinity as n goes to infinity. But analysis has shown this not to be true. Proof: introduce an integer integral power of n. Let a to the n and a be greater than 1, alpha greater than 0, and choose an integer p such that p is greater or equal to alpha. Then our a to the n over n to the alpha is greater or equal to a to the n over n to the p, and it is sufficient to show that a to the n, n to the p goes to infinity as n goes to infinity. So our initial case p equals 2. Since a is greater than 1, a equals 1 plus h, h is greater than 0. Thus, for n greater or equal to 4, we get this here, which is greater than this, which is greater in turn than this. Now n h cubed over 24 goes to infinity as n goes to infinity. Therefore, a to the n over n squared goes to infinity as n goes to infinity. Now, a similar argument can be used to show that for all positive integers p, a of n over n to the p tends to infinity as n tends to infinity. We now have a to the n over n to the alpha goes to infinity as alpha goes to infinity for a greater or equal to 1 and for alpha greater than 0. Now, frequently it is useful to take the reciprocal of a to the n and n to the alpha, since a to the n, n to the alpha goes to infinity as n goes to infinity. It follows that the reciprocal of this will go to 0 as n goes to infinity, for a is greater than 1 and alpha greater than 0. The substitute b equals 1 over a then gives a useful form of the limit, namely n to the alpha b to the n goes to 0 as n goes to infinity for our b contained in 1 and 0. Now if and alpha is greater than 0 by the sandwich rule, this result can be extended to show for a greater than 0 and absolute magnitude of b less than 1 here. And this is our by the sandwich rule. Now as an example here, now if we dividing this through by 8, the top and bottom, we'll get this here. So if these n keeps going on and expanding to infinity, we'll get 0 plus 0 over 0 plus 1 equals 0 as n goes to infinity. And there's another example here with some factorials and powers. Now if we're dividing through again, we'll get 1 plus this term here, this term plus 1. So 1 plus 0, 0 plus 1 equals 1 as n goes to infinity. An example, we find the value of the limit as n goes to infinity for 4 to the 10th power plus r to the n of 1 over raised to the power of 1 over n, where r is any positive real number. And the solution, if r is greater than 0 and 1 is greater or equal to r, then this relationship will hold. Now as n goes to infinity, we get this here, and by the sandwich rule we'll get this one, where all this, as limit tends to infinity of all this equals 1 when dealing with these bounds. If r is greater than 1, then r to the n is tends to infinity as n tends to infinity. So there is an integer n such that r to the n is greater than 4 to the 10 for all n contained in n. It follows that for n greater than n, r equals r to the n raised to the power of 1 over n is less than 4 to the 10 plus r to the n raised to the power of 1 over n is less than r to the n plus r to the n raised to the power of 1 over n, which equals 2 to the power of 1 over n dot r. Now since 2 to the 1 over n goes to 1 as n goes to infinity, the sandwich rule shows that this is true, where r is greater than 1. And that's it for this. Sequences in analysis.